Welcome to 8.6, Systems of Nonlinear Equations. So for us, when they say systems of nonlinear equations, one of them might be linear. Here's an example. Now this is a linear equation. The best way to spot a linear equation is just know it is ax plus by equals c with no exponents on the letters. It's linear. So because of this exponent here, that is not linear. So the system would be considered nonlinear if any part of it isn't linear. This particular system is a line and a parabola. Now, how do we know it's a parabola? Well, from an earlier chapter we know, but you could just rewrite this as y equals 2x squared and know the graph of that. Now, knowing the graph of it and graphing it well enough to actually identify where something, where these two intersect, that would require a very accurate graph if you were just to get out a piece of graph paper and graph this. So in general, I would say that that's not a technique in itself. In other words, just sitting down and graphing, drawing a parabola, even if you thought you were doing it accurately, and then drawing the line. And lines you can draw very accurately, meaning if you know the equation of a line, you can plot 2 points and go through all of the correct points. More confident with that figure, but I'm just going to say the graphing is not a recognized technique for more complicated problems. So we're not going to solve this by graphing, so what are we going to do? Well, we have two choices. Sometimes we can use elimination, the elimination method. The elimination method, now we can't use it on the x's because they are different degrees. There's nothing we could do to subtract and cancel an x and an x squared. But we could cancel the y's. And so that's one way. And the other way is substitution. I'll just kind of walk through both of those real quick. All right, so what the author did was the author took the second equation, the linear equation, equation 1, solved for y, and so you can take equation 2, and if you just kind of follow what we have here, replace y with what y is equal to. So that is the substitution method. You replace y in the other equation with this right-hand side, 2x plus 4. So since we're subtracting y, now we're subtracting 2x plus 4. And that leads to a fairly easy problem to factor and solve. And so what we have are 2 points, and I always remind students, x goes before the comma, so we have 2 points, but all we have are x values. So we have the x values, what we don't have are the y values. But that's fine, we can find the y values by substitution. So let's go back over here, all right. So we use the x values and substitute them into either equation, but they're choosing to put it into this equation. So remember, one of the x values was x equals -1. So we replace x with -1. The other one was x equals 2. We will do that. And so what we've done is we've found the y value for each x value. Get to the final picture, which the author showed on an earlier page. But remember, the point I called A, we knew it was -1, we found out y was 2. And we knew x was 2, we found out y was 8. And so we knew these points, and that does make sense that it intersects twice because, you know, we saw earlier with my kind of crude sketch of a parabola and a line, they might intersect twice. By the way, a parabola and a line might not intersect, and it's even possible for them to intersect one time with what we call a tangent line, where it just touches at one point. So any of those are possible, but what I was saying is, you know, a crude sketch might have told us it was going to intersect twice, but it might not have told us exactly where unless we were very, very accurate with our points. But this actually can help you with an accurate graph. And this is an example of that. So there's no way humanly possible for you to draw a circle and, well, at least this circle and this parabola and know exactly what points they meet in, because these points actually have a square root in the answer, a radical in the answer, so we don't know. And we don't even know that they meet 4 times prior to getting the author's perfect graph. We know that this is a circle of radius 2, because we know how to graph circles at this point. X squared plus y squared equals 2 squared. So we know that circle. And we know this is a parabola, or hopefully we recognize this is a parabola. We've dealt with parabolas in different ways. But the graph isn't what's driving this. I mean, knowing something about the graph can help. I suppose if we knew it was a parabola and a circle, we wouldn't be surprised if we got 4 values for, you know, the intersection, as you can see. But let's just look at the problem. All right. So because the y's are both squared, we can use elimination. So it looks a little unusual, the way they did this. So let me kind of add, for right, x squared plus y squared equals 4. Put the equals 4 way over here. And then let me multiply this by -1. So change the signs. And I'm going to write the minus y squared there. That's going to give me a plus x, because I'm changing signs, equals -4. And I don't know, I just kind of like to see that cancellation. What they did here was they subtracted. I'm adding them together, but I changed the signs. All right. Well, so I do get x squared plus x equals 0, as did they, as did the author, which factors, and I now have my x values for the answers. In the last 2 examples, we found x first. That's not always the case. Sometimes you find y first, and then you have to substitute to find x. But if you find x, put it before the comma. All right. So we're going to substitute each of these values into one equation or the other and solve. It doesn't matter which equation, because remember, the point is in both equations. All right. So if x equals 0, we can substitute that into this equation. They're using equation 2, which is fine. X is 0, so you just get y squared equals 4. So that should say y equals plus or minus 2. Just solving y squared. Y equals plus or minus 2. If x equals 0, so by the way, you might be tempted to think 0 plus or minus 2. And as a human writing that down for another human to grade it, that might work. Can't imagine your, I don't know, calculus professor would mind that. Our problem is we generally don't have access to a plus or minus symbol. So I'll get to how we're going to write that. All right, how about this? If x equals -1, substitute that in on minus -1. So that would be like y squared plus 1, add, subtract 1, I get, okay, y squared equals 3. So now we get y equals plus or minus rad 3. So this is, remember, the starting value with x plus or minus rad 3. And that does tell us there are 4 solutions. I'm going to say that we're not going to leave the plus or minuses there. So write them as separate points. That 0 plus or minus 2, write it as 2 points. I'll call them A and B. And -1 plus or minus rad 3, call those C and D. So 0, 2, so point I'm calling A, points B, C, D, just so you can see what we created there. Even with this, keep in mind, I just found the points. That does not mean I graphed this. So don't confuse the author's, computer drawn graph with our job. Our job was to solve it and to find these points. And so what I mean by that is, realistically, when you type in an answer on a problem like this, it's going to be typing in these points with a comma between every point in the box, of course. So the explanations are nice, and these images are nice, but they weren't required. It was just the author's way of showing us how that works. All right, so we saw substitution, we saw elimination. Let's look at this one. Another system of equations, a hyperbola, and hopefully you kind of recognize that as hyperbola. Maybe not yet, but if I divided it by 4, I'd get y squared over 4, which is 2 squared, minus x squared over 2 squared equals 1. Dividing by 4 would make that a 1. And yeah, that's a hyperbola. And then x equals y squared is a parabola. We know y equals x squared is a parabola open up. This is a parabola that opens to the right. This, by the way, is this hyperbola. If we draw a box that's 2 by 2, well, actually 4 by 4, but it's 2 this way, 2 this way, 2 to the left, 2 to the right, and draw our asymptotes. I am drawing this hyperbola. If it starts with the letter y, we draw it on the y-axis. We put a point on the y-axis. Starts with the letter y, minus then the x. All right, so that was my very crude drawing of these two, and the author gives us this nearly perfect drawing. Not really something we can use other than to say it's interesting. No, we need math, or algebra, not geometry, to really tell what's going on here. But they don't meet, so there is no solution, and that would be the collection or the selection if we were graphing this. But they say either substitution or elimination can be used. When we're using substitution, we can replace y squared with x because y squared equals x. So y squared equals x, I can replace x and just follow what we have. We have x minus x squared equals 4. I did a little work on that, and they found this. Okay, so we want to solve that for x. And when you're solving a quadratic for x, you kind of expect there to be two solutions, but we know there's possible times when there's no solution. And so they actually did run it through the quadratic form. I mean, you can tell it isn't a factor, but run it through the quadratic formula. And this part of the quadratic formula, the discriminant, will tell us if there are any solutions. It turns out that when you run that part through the formula, b squared minus 4ac, you get negative 15. Well, a negative 15 under the radical tells us there are no real solutions, and therefore if there are no real solutions to find x, there are just no points to this problem. So that tells us a lot, tells us that the graphs don't intersect. Again, even if we didn't have the graphs, we would know that. We would know that they don't intersect. So for the most part, there's on the homework, there's a button you can click for no solution. And that's exactly what we do here. The lines don't intersect, or the graphs don't intersect. All right, that is section 8.6, systems of nonlinear equations.